Now that we have derived this equation for orbits of planets around the Sun or satellites around the Earth, it would be nice to take a look at some actual practical applications of this. Unfortunately, celestial mechanics gets very complicated very quickly. First of all, we've already mentioned that if we have more than two bodies involved, we can't actually come up with an analytical solution. This is a two-body problem solution. A third body, we cannot write down anything like this. Moreover, even if we at any one time only have two bodies interacting, many real-life problems still get extremely complicated. For instance, if you want to calculate how to send a probe from the Earth, taking a slingshot around Jupiter and then reaching Pluto, that is a very complex problem. There are, however, a couple of cases where the situation is sufficiently simple that we can actually look at it. And I thought we'd look at one of these here. That's the case of the Holmen orbital transfer. That's a method of putting satellites into orbit, into geostationary orbit, that's used in practice all the time, and it's sufficiently simple that we can derive it right here. Now, to make it possible for us to do this, I'm going to have to make a few assumptions about the thrust that's being applied. So, well, first of all, before we do any of that, there are a couple of terms that I haven't mentioned to you yet that you need to know. This is now the Sun or the Earth, and here's a satellite or a planet that's going around it. This point closest to the Sun or the Earth, that's known as the Perigee in the case of a planet, or perihelion for a sun. And the opposite position, where the satellite or planet is at its farthest location from the Sun or the Earth, that's known as apogee or aphelion, depending on whether this is a planet or a sun, respectively. But now we're working with the Earth, and just to indicate that, I'm going to change the color here of the central body to something that's a bit more Earth-like, blue perhaps. Okay, so this is now the Earth. That's a satellite. Just remind you of a couple of things. This distance here between the center of the ellipse, if you have an elliptical orbit, and the location of the focus, that distance d is given by a times epsilon. Also, the perigee is the point of closest approach, so that's the same thing as the minimum r. So we can say that r minimum equals 1 over 1 plus epsilon, right? Because the maximum value cosine can have here is 1, and it gives us the smallest r. That's the perigee, r peri. The maximum r, similarly, is 1 over 1 minus epsilon. That's the r at apogee. Okay, so now in order to make this work, what I'm going to do is make a few assumptions on the thrust that we're going to apply to the satellite. Because what we're going to do here is figure out a way of changing the orbit of a satellite that's already orbiting around the Earth. And to do that, we apply thrust, right? So we have a few assumptions about that thrust. First of all, we're going to assume that it's instantaneous. In other words, it takes no actual time to apply the thrust, so that the orbital position of the satellite doesn't change during the thrust. It's applied at apogee or perigee, not at any other position. And at this point, of course, there is no change in r, which makes things simpler. And finally, we assume the thrust is purely angular. That is, it has no radial component. So when you deliver a thrust here, all that you're accomplishing is that you're changing the velocity of the satellite, but you're not changing the direction of its motion. keeps moving in the same direction, and that direction at perigee and apogee is perpendicular to the direction to the Earth. So what that means is that if you apply a thrust, you will either the thrust will either be in the forward direction, in which case you will move faster here, and as we'll see in a minute, this means that the orbit becomes more eccentric, or we can have a backwards thrust, and that means that the orbit becomes less eccentric. Okay, but that's a bit of a preview, so I'm going to delete that here. So let's say here that we start at perigee, and then after we're done, we end up at a perigee still. Or we could be now at apogee. If we slow down sufficiently, the old perigee could become the new apogee, as we'll see. Now, because all we're doing here is changing the velocity, we are not changing the r. Right? So remember, we're going from one r minimum to a new r minimum, or to an r maximum. So we have that before the thrust is applied, we have some C1. And again, I'll remind you that C equals L squared over gamma mu. So we have C1 divided by 1 plus the initial eccentricity. And that's going to be equal to now C2 divided by 1 plus the final eccentricity, epsilon 2. And we're also going to say that the thrust involves a change in velocity, okay, that we're going to parameterize with a coefficient lambda. So that we go from some V1 here to some V2 that are related such that V2 equals lambda times V1. Okay. The other thing we know is that when we're at perigee or apogee, the expression for the angular momentum, and that's L here, is particularly simple because the velocity is perpendicular to the direction towards the Earth. It's just given by the reduced mass mu times r times v. So because of that, we can also say that L2, the angular momentum afterwards, that is part of C2, is equal to lambda times L1. And then because of the definition of C here, this gives us that C2 equals lambda squared C1, right? Because C is proportional to L squared. So we can then take this result and plug it in here. So we get just that C1 divided by 1 plus epsilon 1 equals lambda squared C2 divided by 1 plus epsilon 2, right? No. C1 is what we get here. That's kind of the whole point. So that means that the C1s here go away. And we're left with the expression 1 plus epsilon 1 equals 1 over lambda squared times 1 plus epsilon 2. And then we can use this to solve for epsilon 2. Just multiply by lambda 2 here, and then bring the 1 over on the other side. We will find epsilon 2 equals lambda squared times epsilon 1 plus lambda squared minus 1. Okay. So that's our intermediate result. So from this we can see now that if lambda is greater than 1. That is, if we increase the velocity, if we have a forward thrust, that means that epsilon 2 is greater than epsilon 1. So that corresponds to an increase in the eccentricity, just like we said. Similarly, if lambda is less than 1, that is a backward thrust, then epsilon 2 is less than epsilon 1. So that's a decrease in eccentricity. Just like this figure showed. Right? Forward thrust, more eccentricity. Backwards thrust, less eccentricity. And in fact, if we have sufficiently small lambda, that will give us epsilon 2 less than 1, less than 0, a negative epsilon 2. So what has happened then is the perigee has become the new apogee. Basically, what used to be the closest distance has become the farthest distance. Remember, our maximum is 1 over 1 minus epsilon. And that's what happens when epsilon changes signs. So let's apply this to the actual case of the Hohmann orbital transfer. What happens in that case is the following. That's illustrated by this figure here. So we are starting out in a low Earth orbit. We're moving around the Earth here at relatively low altitude in a circular orbit. So this is the low Earth orbit, and the radius of that orbit is r Leo for low Earth orbit. Then at some point here you apply a momentary thrust to your satellite in the forward direction, which throws your satellite into this geostationary transfer orbit. Geostationary transfer orbit, like this. Although you don't make a full elliptical orbit, actually once you get to the apogee, you apply a second thrust, this time in the backwards direction, and you reach this blue orbit here, which is the geostationary Earth orbit, or GEO. So its radius is r GEO, like that. So like I mentioned, over here we have some initial delta V. Delta V first, so the first maneuver, and then you move around here, and now you're going to have a second delta V here associated with a second maneuver. So two different thrusts, each of which is known as a maneuver, which puts the satellite from a low Earth orbit to geostationary transfer orbit. Okay. So to help with this, I'm going to copy a couple of things from up here. I'll delete that again to give some space. You won't need that. And hopefully you can remember these terms. All right. So let's see how we calculate this. In order for us to be able to apply this formula here, this one, we have to first figure out what the epsilon 1 and epsilon 2 are for the two maneuvers. So we'll look first at the first maneuver here. In this case, we have epsilon 1 is going to be 0, and epsilon 2 is something we don't know and we have to figure out. But although we don't know epsilon 2, we do know the radii of the low Earth orbit and the geostationary transfer orbit. I'll give you the numbers in a minute, but we do know those. So we can use the formulas that we know, particularly this one, in order to figure out what epsilon 2 might be. So if you look here at this ellipse is the same as this one, essentially. It has a semi-major axis, so of length a. So we can see that the distance from apogee to perigee is 2a. Right, we can see that. We can also see that the distance from apogee to perigee here is the low Earth orbit radius plus the geostationary transfer orbit radius, plus the geostationary Earth orbit radius, right? So we have that, looking at the distance from perigee to apogee, we get that that's 2a, or R Leo plus R Geo. So that's one thing that we know. The other thing we can see is that this parameter d here for this ellipse, that's equal to the R Geo minus the semi-major axis again. So R Geo equals a plus d, but d is a times d times epsilon here. So this is a times epsilon 2 in this case, because we're going from a circular orbit to an elliptic orbit. So now we can use this to solve our problem. Well, first we have to realize that this is actually wrong. I forgot to add in a, obviously. That's a very simple error I shouldn't make. Okay, so this is a times 1 plus epsilon 2. In other words, a is R Geo divided by 1 plus epsilon 2. We can plug that into this expression, and we will get So with the help of this result, we can now calculate what epsilon 2 should be if we just know the parameters for the R Leo and R Geo. And we do. The geosynchronous Earth orbit, or geosynchronous equatorial orbit, has a radius of 42,164 kilometers. Now the low Earth orbit, that might vary depending on what kind of vehicle you use in order to put it into this orbit, but roughly an altitude of 1,000 kilometers is reasonable. Since the Earth has a radius of about 6,400 kilometers, that means that R Leo we can take to be 7,400 kilometers. Okay, so you plug those numbers in to this formula here, and you will get, with a little bit of work, that epsilon 2 in this case is 0.701. That's the eccentricity of that orbit. Alright, so now let's remind ourselves of some things. We have this expression over there. This is true. And in our first maneuver here that we're undertaking, we're starting with epsilon 1 equals to 0. And epsilon 2, we don't know what it is. Well, actually, we do know what it is now. It's 0.701. Right? So now we can actually figure out what lambda is. given that epsilon 1 is 0, what we're left with is just epsilon 2 equals lambda squared minus 1, or lambda is the square root of 1 plus epsilon 2, which turns out to be 1.304. So we have a boost of 30.4%. All right. That's the first maneuver that we just undertook here. All right. Now we'll need to go to the second maneuver. That says maneuver, if you can read it. So now we're actually starting in elliptical orbit. So epsilon 1 is going to be non-zero. Epsilon 2 will be 0, though, because our goal is to go into a circular orbit. Moreover, we are at the apogee. And that means that in order for our formulas to work, we have to use a negative epsilon. Right. So we have that epsilon 1 equals minus 0.701, and that epsilon 2 equals 0. Okay, and we can then again plug this into this formula up there, in which case we will obtain, just underline that the way I did before, we will get that 0 equals lambda squared epsilon 1 minus 1. Actually minus 1 plus lambda squared, of course. So lambda squared 1 plus epsilon equals 1, and therefore lambda in this case, so this is lambda for the first maneuver, lambda for the second maneuver is 1 divided by the square root of 1 plus epsilon 1, which remember now is negative. So this becomes the square root of 1 minus 0.701, and if you calculate that out, you get 1.83, or in other words, an 83% boost. And I realize that means, of course, that we have to change the direction of this booster. It's not in the backwards direction, because we are, in this case, actually increasing epsilon from a negative value to a positive value. So the boost here is also in the direction of travel. So that was a mistake. Okay. All right, so 83% boost. What does that correspond to in actual velocities? Well, we can calculate that really quickly. I'm not going to show it here, but we can show that in a circular orbit, we know that the velocity is going to be the square root of gm over r. You can derive that as an exercise. So delta v in the first instance is therefore going to be lambda first minus 1 times gm divided by r low Earth orbit. So 0.304 times the square root of 6.67 times 10 to the minus 11, and then you multiply that by the mass of the Earth, 5.972 times 10 to the 24, I believe. Divide that by radius of low Earth orbit, 7.4 times 10 to the 6 meters. That's what we got here, right? 7,400 kilometers. And if my calculations are correct, then that equals 2,230 meters per second. Now, to calculate delta V in the second case is a little bit different. To come up with this formula, we use that V2 equals lambda times v1. And in this first case here, we knew v1 because v1 was was v Leo. Right? That means that delta v first, which is v2 minus v Leo, equals lambda minus 1 times v Leo. And that's that formula here. For the second maneuver, what we know is actually v2. Right? So in the second maneuver, we have that vGO equals lambda times some unknown v1. And that means that delta v second equals vGO minus v1, which we don't know. So that is then vGO times 1 minus 1 over lambda. VGO is otherwise given by the same thing here, so we get 1 minus 1 over 1.83 times the square root of GM divided by R. GO, and a little bit of plugging in then gives us 1,390 meters per second. So it's actually a smaller boost here in meters per second, which is interesting, given that the actual boost in terms of percent is higher. Whereas in the first maneuver we had 2,230 meters per second. That was the boost, but it corresponds to only a change in velocity of 30%. The reason for that is, of course, that the velocity in a circular orbit is inversely proportional to the square root of the distance. So in this graph here, in the outer orbit, the motion is much slower than in the inner orbit. So in low Earth orbit, it might take an hour and a half to go around the Earth. Here, by definition of the geostationary Earth orbit, it takes 24 hours, so that the satellite remains located above the same patch of land on the Earth at all times.